S block elements. The elements belonging to group 1 and 2 of the periodic table are called S block elements. These have one or two electrons in their outermost s orbital. Group 1 elements are called alkali metals and have the general electronic configuration NS1. These constitute six elements, namely lithium, sodium, potassium, rubidium, cesium, and francium. These are called alkali metals because they readily form oxides and hydroxide, which are alkaline. The group 2 elements of the periodic table are called alkaline earth metal and they consist of the elements beryllium, magnesium, calcium, strontium, barium, and radium. Their general electronic configuration is Ns2. These elements of group 2 are also metals. The oxides of some of the metals were known much earlier than the metals themselves, and these were called alkaline earth metal because they were alkaline in nature and exist on the earth. In the present unit, we will have a complete comparative study of the elements of these two groups and some of their salient features. The abundance and occurrence. The alkali and alkaline earth metals are the most violently active of all the metals. These are readily oxidized and therefore are not found in the free state in nature. These are found in the combined form with halide, sulfate, carbonate, silicate, cyan, etc. The abundance of alkaline and alkaline earth metal in the earth crust shows a good range. Among these, calcium is the fifth most abundant element in the earth's crust and hence the third most abundant metal after aluminium and iron. Vast sedimentary deposition of calcium carbonate occur over large parts of the Earth's surface. Magnesium is the sixth and sodium is the seventh most abundant element in the crustal rocks. These are fourth and fifth most abundant metals after aluminium, iron, and calcium. Potassium is the next most abundant element after sodium. There is unlimited supplies of NaCl in natural brines and oceanic waters. The occurrence of other metals in the Earth's crust is very poor. Francium and radium are radioactive and have rare terrestrial abundance. Beryllium is rare and radium is the rarest of all, comprising only 10 to the power minus 10% of igneous rocks. The physical properties of group 1 elements. First is atomic and ionic radii. Alkali metals have the largest atomic and ionic radii in their respective periods. On moving down the group, the atomic and ionic radii increases. This is due to the fact that alkali metals are the first elements of each period. As we move in a period, the atomic radius and ionic radius tend to decrease due to increase in the effective nuclear charge. Therefore, the alkali metals have the largest atomic and ionic radii in their respective periods. On moving down the group, there is increase in the number of shells and therefore atomic and ionic radii increases. Second is ionization energies. Alkali metals have the lowest ionization energy in each period within the group. The ionization energy of alkali metal decreases down the group. The atoms of alkali metals are largest in their respective periods and therefore the valence electron are loosely held by the nucleus. By losing the valence electron, they acquire stable noble gas configuration. This accounts for their ease to lose electron and hence they have low ionization energies. Or moving down the group, the atomic size increases and the magnitude of screening effect, number of inner shells also increases and consequently the ionization energy decreases down the group. The second ionization energy of alkali metals are very high. When an electron is removed from the alkali metals, they form monovalent cations which are very stable electronic configuration, same as that of noble gas. Therefore, it becomes very difficult to remove the second electron from the stable gas configuration and hence their ionization energy values are very high. Third is melting and boiling point. All these metals are soft and have low melting and boiling points. The alkali metals have only one valence electron per metal atom and therefore the energy binding the atoms in the crystal lattice of the metal is low. Thus the metallic bonds in these metals are not very strong and consequently their melting and boiling points decreases on moving down from lithium to scandium. Fourth is density. The density of alkali metals are quite low as compared to other metals. Lithium, sodium, and potassium are even lighter than water. The density increases on moving down the group. However, potassium is lighter than sodium. The densities of metallic elements depend upon the type of packing of atoms in metallic state and also on their size. The alkali metal have close packing of metal atoms in their lattice, and because of the larger size of their atom, they have low densities. As we move down group from lithium to scrantium, there is increase in atomic size as well as in atomic mass, but the increase in atomic mass is more than compensate the increase in atomic size. As a result, the densities mass per volume of alkali metals gradually increases from lithium to scrantium. However, potassium is lighter than sodium, probably due to larger increase in atomic size as compared to increase in atomic mass. It may be noted that it is quite unusual for metals to have low densities. For example, most of the transition metals have very high densities, generally more than 5 gram per centimeter cube. For example, iron has a density of 7.9 gram per centimeter cube, while mercury has a density of 13.6 gram per centimeter cube. Next is electropositive or metallic character. All the alkali metals are strongly electropositive or metallic in character. The electropositive character of an element is expressed in terms of the tendency of its atom to lose electrons. As alkali metal have low ionization energies, their atoms readily lose their valence electron. These elements are therefore said to have strongly electropositive or metallic character. Since the ionization energy decreases down the family, the electron releasing tendency or electropositive character is expected to increase down the family. Sixth is oxidation states. All the alkali metal exhibit an oxidation state of +1 in their compound. The alkali metals have only one electron in their valence shell, and therefore they can lose the single valence electron readily to acquire the stable gas configuration. They form monovalent ions M positive, for example Li positive, Na positive, K positive. Since the second ionization energies are very high, they can form divalent ions, thus alkali. So they can't form divalent ions, thus alkali metals are univalent and form ionic compounds. Seventh is characteristic flame coloration. All the alkali metals and their salt impact characteristics flame coloration. The alkali metals have very low ionization energies. The energy from the flame of Bunsen burner is sufficient to excite the electrons of alkali metals to higher energy levels. The excited state is quite unstable, and therefore when these excited electrons come back to their original energy levels, they emit extra energy which fall in the visible region of the electromagnetic spectrum and thus appear colored. The different colors of the alkali metals can be explained on the basis of amount of energy absorbed for excitation of the valence electron. Next is photoelectric effect. The alkali metals readily emit electrons when radiation strikes on their surfaces. This phenomena of ejection of electrons when electromagnetic radiation strikes on the surface of metal is called photoelectric effect. Because of low ionization energies, the electrons of alkali metals can be easily ejected from their surfaces. Among alkali metals, cesium has the lowest ionization energy and hence it can show photoelectric effect to the maximum extent. Therefore, alkali metal, especially cesium, are used in photoelectric cells which are sensitive to blue light. Next is nature of the compound. The compound of the alkali metal are ionic in nature due to the low ionization energy and large atomic sizes. The atoms of alkali metal form cation readily by losing the valence electron. Consequently, they form ionic bonds with the known metals of the p block. Next is lattice energies. Lattice energies. The alkali metals salt consist of cation and anions which are held by strong electrostatic force of attraction. Therefore, the lattice energies of alkali metals salts are very high. The lattice energy is defined as the amount of energy required to break 1 mole of crystal into free ions. Therefore, lattice energy gives a measure of the force of attraction between the ions. Larger the force of attraction, the greater will be the lattice energy. The lattice energy also depends upon the size of the ion and its charge. For the cation of the same energy, the lattice energy of ionic solid having the same anion decreases, while increasing in size the cation due to decrease in the force of attraction between them as shown below. The chemical properties. The alkali metal exhibits high chemical reactivity. It is due to the their low ionization energies and low heat of atomization. As the value of ionization energy decreases down the group from lithium to scandium, therefore the reactivity of alkali metal increases from lithium to scandium. The alkali metal are strongly highly reactive towards the more electronegative elements such as oxygen and halogen. Some of their characteristics chemical properties are given below. First is action with the air. All the alkali metals get tarnished on exposure to air due to the formation of oxide at the surface. They burn vigorously in air or oxygen, forming three types of oxides: normal oxide containing O2 negative oxide ion, peroxide containing O2 2 negative ion, superoxide containing O2 negative superoxide ion. When the metals are burned in a freely supply of air, the main product depends upon the metal. Lithium forms only the oxide Li2O. Sodium form peroxides, while potassium, rubidium, and cesium form superoxides. Now question arises as to why lithium forms only normal oxide, sodium forms peroxide, and while other forms superoxide. The formation of stability of these oxides can be explained on the basis of the size of cation and the anion. It is known that smaller cation can stabilize smaller anion and larger cation can stabilize larger anion. This is the basis of lattice energy effects. The normal oxide contains O2 O2 negative ion. The peroxide contains O2 2 negative ion and superoxide contains O2 negative ion. Lithium ion is very small ion and therefore has strong positive field around it. Therefore, it can stabilize only a small ion anion. In other words, because of small size of lithium ion, the spreading of negative charge towards another oxygen is prevented and therefore it can't be attached with another oxygen atom. Consequently, higher oxide are not formed. Sodium ion is larger and it can stabilize larger anion. The positive field around sodium ion is weaker and does not prevent the conversion of oxide into a peroxide ion, but it is stronger enough to prevent further oxidation to superoxide ion. On the other hand, because of larger size of K positive, R positive and Cs positive ion, the positive field is very weak and allows the superoxide ion to be formed. These are briefly discussed below. A oxides pure Li2O prepared by thermal decomposition of Li2O2 at 450 degrees Celsius. Sodium oxide Na2O is prepared by the reaction of NaOH and Na2O2 or NaNO2 with sodium metal. The normal oxide of other alkali metal can also be prepared by similar reactions. Li2O and Na2O are white, K2O is yellowish, while Rb2O is bright yellow and Cs2O is orange. They are fairly stable towards the heat and decompose only above 500 degrees Celsius. Peroxide. The peroxide contains peroxide ion O2 2 negative, which is isoelectronic with F2. Li2O2 is prepared industrially by the reaction of LiOH, S2O and S2O2 and dehydration of the subsequent hyperperoxide by slightly heating under reduced pressure. Superoxides. These contain the paramagnetic O2 negative ion, which is stable only in the presence of larger cations such as potassium, rubidium, scandium and NaO2 is prepared by the reaction of O2 with sodium dissolved in liquid NH3. It can also be prepared by reacting Na with O2 at 450 degrees Celsius and 150 atmospheric pressure. Other heavier alkali metal superoxide can be obtained by burning these elements in air. Now the second is action with hydrogen. The alkali metals react with hydrogen to form hydrides which are ionic in nature. The reactivity of alkali metal with hydrogen increases from lithium to scandium. The ionic character of the hydrides increases from lithium to scandium. This is because of decrease in ionization energy down the group so that electrons becomes easily available to hydrogen for forming H negative ion. The stability of hydrides decreases from lithium to scandium. This is due to the fact that as the size of the alkali metal increases lithium to scandium so that the MH bond becomes weak. Therefore, the stability of hydrides decreases. The hydrides reacts with water, liberating hydrogen. Lithium hydride is used as a source of hydrogen for military purpose and for filling meteorological balloons. The hydrides behave as strong reducing agent and their reducing nature is increases down the group. The next is action with water. Alkali metal readily react with water to form hydroxide and hydrogen gas is evolved. As the electropositive character increases down the group, the reactivity with water increases on descending the group from lithium to scandium. The hydroxide of alkali metal are strongly basic and the basic strength increases down the group. Next is the action of halogens. The alkali metal readily combine with halogen to form ionic halides. The reactivity of halogen towards alkali metal increases on moving down the group. This is due to increase in ionization energy or increase in electropositive character as we move down the group. LiF is insoluble in water due to its high lattice energy because of small cation and small anion. Next is solutions in liquid ammonia. Alkali metals dissolve in liquid ammonia to give blue solutions which are conducting in nature. In solution, the alkali metals atom readily loses the valence electron. Both the cation and the electron combine with ammonia to form ammoniated cation and ammoniated electron. Due to the presence of free or ammoniated electrons, these solutions behaves as strong and valuable, powerful and selective reducing agents. These solutions can reduce aerial oxygen to superoxide and peroxide ions without bond cleavage. Next is reducing nature. Alkali metal are strong reducing agents. This is due to the greater extent to lose electrons. The next is anomalous behavior of lithium and diagonal relationship. Though lithium belongs to the alkali metals group 1 and has the most of the characteristic properties of the metals of group 1, however it differs from the remaining members of the group in many respects. It is mainly due to the following reasons. The size of lithium atom and its ion is very small. It has very high ionization energy and least electropositive character. The third is the polarizing power of Li positive ion is quite high due to its small size, which results in the covalent character of compounds. It has no vacant d orbital in its valence shell. Some of the important characteristics of between lithium and the rest of family members are given below. Lithium is the hardest of all the alkali metals. The melting and boiling point of lithium are much higher than those of other elements. Lithium is less reactive as compared to other metals and it doesn't get tarnished readily. It forms only monoxide with oxygen, while sodium forms peroxide and other elements form superoxide. The salt of lithium have lower ionic character and salts of other alkali metals. It is because of high polarizing power of Li positive ion. It readily reacts with nitrogen form nitride, while other metals don't react. Only lithium combines with carbon and silicon form the carbide and the silicide. Lithium hydroxide and carbonate are unstable and decompose on heating, while the corresponding compounds of the rest of the family members are stable and don't decompose. Upon heating, lithium nitrate gives nitrogen dioxide and oxygen. The hydride of lithium is more stable as compared to the hydrides of other members of the family. Lithium chloride and nitride are soluble in alcohol, while the salts of sodium are insoluble in alcohol. Lithium hydroxide is much less basic than the hydroxide of other metals. Lithium fluoride, carbonate, hydroxide, oxalate, and are springly soluble in water. The corresponding of salts of sodium and potassium are readily soluble. The Li positive and its compounds are more heavily hydrated than those of sodium. However, lithium show diagonal relationship with magnesium. Diagonal relationship, it has been observed that some of elements of the second period show similarities with the elements of the third period present subsequently to each other, though belonging to different groups. It is known as diagonal relationship. Thus, the similarity in properties of elements present diagonally is called diagonal relationship. This is shown below. For example, lithium resembles magnesium, beryllium resembles aluminum, and boron resembles silicon. Cause of diagonal relationship. The cause of diagonal relationship is the similarity in properties such as electronegativity, ionization energy, size of atom or ion, electropositive character, polarizing power, etc. as discussed below. First is similar positive character, electropositive character. As we move from left to right in a period, electropositive character decreases, and while going down a group, electropositive character increases. Therefore, on moving diagonally, the two opposing tendencies almost cancel out. The electropositive character in is almost same as we move diagonally. Second is polarizing power. On moving left to right in a period, the ionic charge increases while the ionic size decreases, thus causing an increase in polarizing power. On the other hand, on moving down a group, the ionic charge remains the same while the ionic size increases, and therefore the polarizing power decreases. As a result of these two opposite changes on moving diagonally, these two effects partially cancel each other, and therefore the two elements have almost similar polarizing power. Thus, the two elements have almost similar properties. Diagonal relationship between lithium and magnesium. Lithium, which is quite anomalous in characteristic as far as alkali metals are concerned, exhibits diagonally similar with magnesium, the second member of group 2 present in the third period. The common characteristics of these two elements are listed below. The atomic radius of Li is 1.23 angstrom, while that of magnesium is 1.60 angstrom. The ionic radius of Li positive ion is quite close to that of Mg2 positive ion. Both these metals are quite hard in nature. The electronegativities of lithium and magnesium are not much different. Both lithium and magnesium ion have polarizing power of almost same magnitude. Both LiOH and MgOH hold twice are weak bases. Lithium forms monoxide. Magnesium also prefer to form only the monoxide MgO. The carbonates of both the elements evolve carbon dioxide on heating. The hydroxide of both these elements decompose on strong heating. The hydroxide of other alkali metal are stable to heat. The nitrates evolve nitrogen peroxide and oxygen upon heating. Both Li and Mg react with nitrogen to form corresponding nitrates. Lithium chloride, like magnesium chloride, is deliquescent. Lithium hydroxide, like magnesium hydroxide, is a weak base. Lithium hydroxide, fluoride, phosphate, oxalate, and carbonate are much less soluble than the corresponding sodium and potassium salts. However, the solubilities are compared of those of corresponding magnesium salts. Here is the physical properties of group 2 elements, atomic and ionic radii. The atomic and ionic radii of the members of the family are smaller than the corresponding members of the alkali metals. The alkali earth metals have a higher nuclear charge and therefore the electrons are attracted more towards the nucleus. As a result, their atomic and ionic radii are smaller than those of alkali metals. On moving down the group, the radii increase due to gradual increase in the number of the shells and the screening effect. Next is density. Alkali earth metal have low densities but are relatively more dense than alkali metals. This is because their atomic sizes are smaller than the corresponding alkali metals. Density decreases on moving down the group up to calcium, but it then increases considerably up to radium. Third is melting and boiling points. Alkali earth metal have low melting and boiling points while are higher than the corresponding alkali metal in the same period due to comparatively small size. However, melting and boiling point don't show regular trends. The atoms of alkaline earth metals have smaller size as compared to alkali metals. Therefore, they are more closely packed in their lattice and hence they have higher melting and boiling points. Next is the ionization energy. The alkali earth metal have low ionization energy due to fairly large size of the atom. Since the atomic size increases down the group, the ionization energy decreases. A comparison of the ionization energy of the members group 1 and 2 show that the members present in the second group have higher values as compared to those of group 1 because they have smaller size and electrons are more attracted towards the nucleus of the atoms. Next is the electropositive and metallic character. Because of the low ionization energy of alkali earth metals, they are strongly electropositive in nature. However, these are not in strongly electropositive as that of alkali metals of group 1 because of comparatively high ionization energies. The electropositive character increases down the group from Be to Ba. Next is characteristic flame coloration. Except for beryllium and magnesium, the alkaline earth metal salts imparts characteristic colors to the flame. Now the chemical properties. Because of their low ionization energy and high electropositive character, the alkaline earth metal have strong tendency to lose valence electron. Therefore, they are very attractive. The reactivity of these elements increases on going down the group. However, alkaline earth metal are in general less reactive than alkali metals. The chemistry is mainly dominated by the dipositive oxidation state. Some of the general trends are discussed below. First is action with air or oxygen, formation of oxides. The alkaline earth metals, being less electropositive than the alkali metals, react to air or oxygen slowly upon heating to form oxides. The reactivity with oxygen increases as we move down the group due to increases in electropositive character of the elements. The monooxide can also be prepared by decomposition of their carbonates. Among the oxides, beryllium is amphoteric while oxides of other elements are basic in nature. The increase in basic character of oxide from beryllium to barium is because of decrease in polarizing power with increase in ionic size. Next is combustion with hydrogen, formation of hydrides. All the elements except beryllium combine with hydrogen upon heating to form ionic hydrides MH2. Next is action with water. Formation of hydroxide. The alkaline earth metal have lesser tendency to react with water as compared to alkali metals. They combines with water slowly to form hydroxides. Magnesium don't react with cold water but it decomposes hot water. Like alkali metals, the hydroxide are basic in nature and basic strength increases down the family. Next is the Action with nitrogen. The alkali earth metal react with nitrogen to form nitrides, which react with water to liberate nitrogen. Next is formation of halides. All the alkaline earth metal combined with halogen at higher temperature forms their halide. The metal halide can also be obtained by the action of halogen acid on metals, their oxides, carbonate, and hydroxide. Anhydrous beryllium halides can't be obtained from materials prepared in aqueous solution because of the formation of hydrated ion. The dehydration of these products result in hydrolysis. The anhydrous beryllium fluoride and chloride can be prepared by the following methods. Next is the anomalous behavior of beryllium and magnesium and diagonal relationship. Beryllium, the first member of the alkaline earth metal family, show anomalous behavior as compared to magnesium and the rest of the members. However, beryllium shows diagonal relationship with aluminium. It is mainly because of the following reason: small size of the atom or its sign, high ionization energy and electronegativity, absence of d orbital. Some of the important differences between beryllium and magnesium are given below. Beryllium is harder than magnesium. It possesses higher boiling point and melting as compared to magnesium. Beryllium does not react with water even at elevated temperature. On the other hand, magnesium reacts with boiling water. Beryllium does not combine directly to form hydride, whereas magnesium does. The next is beryllium forms covalent compounds with magnesium form ionic compounds. Beryllium carbonide with water gives methane while magnesium carbonate gives acetylene. Barium oxide is amphoteric in nature while magnesium oxide is basic. Diagonal similarities of beryllium and aluminium. Beryllium shows similarities with aluminium due to diagonal relationship. Some common examples are both barium and aluminium. Both beryllium and aluminium form covalent compounds. Beryllium and aluminium is rendered passive on treatment with concentrated HNO3. Both form complexes. Beryllium oxide and aluminium oxide are amphoteric, that is, they dissolve in acid and as well as bases. The carbides of both boron and aluminium liberate methane with water. Both the metals are weakly electropositive in nature. Beryllium and aluminium form fluorocomplex ions in solution. The other group 2 metals don't form stable fluorocomplex in solution. Beryllium dissolves in alkaline to form berylate ion, while aluminium dissolves to give AlOH 6 3 negative. Beryllium chloride and aluminium chloride had a bridge polymeric structure. Halides of both beryllium and aluminium have similar solubilities. Here's the special features of hydrides of S block elements. All alkali metals combine with dry hydrogen to form hydrides of the general formula MH. The hydrides of alkaline earth metal are also prepared by heating metals with hydrogen. Beryllium hydride is prepared as barium chloride plus lithium hydrides in the presence of ether leads to beryllium hydride. Other elements of group 2 directly combine with hydrogen to form ionic hydrides. Calcium hydride is commonly known as hydrolith. Alkali metal hydrides are crystalline solid because they have ionic structure. The ionic character of the hydrides increases as we go down the group. These hydrides are not very stable. They react with water readily, liberating hydrogen. Lithium also forms complex hydrides, which is used as a reducing agent. It is obtained from lithium hydride and in dry ether. Sodium also forms complex hydrides. It is best prepared by heating sodium hydride with trimethyl borate. It is also used as a reducing agent. Therefore, these hydrides are used as reducing agent. In general, the reactivity of these hydrides increases down the group and therefore their reactivity character are follows the same trend. In case of alkaline earth metal hydrides, BeH2 is covalent while MgS2 is partially ionic. The hydride of calcium, strontium and barium are largely ionic due to larger electropositive character of the metals. The alkaline earth metal hydrides are reducing agent and are hydrolyzed by water liberating hydrogen. Therefore, they can also act as reducing agent. BeH2 and MgS2 are examples of polymeric solids. Polymeric has very interesting structure as shown in figure 4. Beryllium is bonded to 4 hydrogen atoms and hydrogen is forming 2 bonds. The bond between 2 beryllium atoms and 1 hydrogen atom is a special type of bond, has 3 center pair bonds, also called banana bond. It covers 3 atoms. And now the role of alkaline earth metal ion in biological systems. Role of Na positive and K positive ion. Na positive and K positive ion play a very important role in living organisms, including human beings. Though sodium and potassium are quite similar in their chemical properties, yet their biological functions are very different. Na positive ion is a major cation of extracellular fluids of living organism, which activates certain enzymes in the body. The Na positive ion are actively expelled from the cell, whereas K positive are not. This ion transport is called sodium pump and is involve both the active explosion of Na positive and take up K positive ion. As a result of this, it expels Na positive ion from intracellular fluids to the extracellular fluids with the help of carrier proteins. At the same time, it takes up K positive ion into the intracellular fluids. Analysis of the fluid inside and outside animal cells show that this type of anion transport rarely occurs in animal cell. The concentration of K positive ion is about 0.15 molar and that of Na positive is about 0.01 molar in the body fluids outside the cells. The concentration of K positive and Na positive ion are about 0.004 m and 0.15 molar respectively. The energy required for the transport is obtained by the hydrolysis of ATP. It has been estimated that hydrolysis of one ATP molecule to ADP provides energy sufficient to expel 3 Na positive ions out of the cell and 2 K positive ions back to the cell. Since each operation of the pump expels large number of Na positive ions from the cell, then the number of K positive ions that it pumps into the cell acquires an excessive negative charge and the exterior of the cell acquires an excessive positive charge. This results in the development of electric potential across the cell membrane, which is responsible for the functioning of nerve and muscle cells. K positive ions inside the cells are essential for the metabolism of glucose, synthesis of protein, and activation of some enzymes. Role of Mg2 positive and Ca2 positive ions. As already studied, magnesium is an important constituent of chlorophyll, which is responsible for photosynthesis in green plants. Mg2 positive ions are concentrated more in the intracellular than in the extracellular fluids in animals' bodies. On the other hand, Ca2 positive ions are concentrated more in the body fluids outside the cell, similar to K positive ion and Na positive ions. The the Mg2 positive ion helps in the activation of phosphate transfer enzymes which participate in the energy releasing biochemical process occurring in animal bodies. Magnesium ion are also required for carbohydrate metabolism. Mg2 positive and Ca2 positive are responsible for the transmission of electrical impulse along the nerve fibers and for the contraction of muscles. Calcium ion are essential for the formation of bones and teeth as a apatite and the enamel on teeth as a fluoroapatite. Ions are important in blood clotting and for the maintaining the regular beating of the heart. Certain types of muscle cramps are prevented by increasing the intake of Ca2 positive ions.